That's going to be 3 cubed. It's going to be 27. So this is going to be a negative number. So my f double prime of 0 is going to be negative. So that tells me that my original function is concave down. Okay. So then if we test from 1 to infinity, we can test x equals 2. So then our f double prime of 2 is going to be 36 times 2 squared minus 1 divided by 2 squared plus 3 cubed. Let me see, that's going to be 4 minus 1 is 3, 90, 108. Let's see, 4 plus 3 is 7 cubed. Alright, so that's again positive. So that tells us that f double prime of 2 is positive. So this tells us our original function is concave upward. Okay. Okay. So again, with example 2, it says determine the intervals on which the graph of the function is concave up or concave down. So again, we looked at f double prime. If we're talking about concavity, we need to look at f double prime. We found the values for which so f double prime we got here. We found the values for which this f double prime was 0, was 1 and negative 1. Those will make it 0. And there weren't any numbers that's going to make our denominator 0. So we only chose negative 1 and 1, and we tested those intervals. We chose negative 2, we chose 0, we chose 2. And that told us that whether the interval was concave up or concave down. All right. So far we've talked about where the functions can be concave up or concave down, but what happens if the concavity changes? So what if you have a point where on one side it's concave up, on the other side it's concave down? When you have something like that, we call those points of inflection. So we have that if the tangent line to a graph exists at a point at which the concavity changes, then that point is called a point of inflection. Okay. So like for instance, if you look at this one on the left, we're saying that this point here is a point of inflection. On the left, the function is concave up. On the right, the function is concave down. We have a tangent that exists where on the left is up and on the right is down. This is called a point of inflection. This is another example. If you draw a tangent line here, it looks like this. Again, on one side of the tangent is concave down, on the other it's concave up. So this point is a point of inflection. And the same goes for the third. So a formal definition of point of inflection. If the graph of a continuous function has a tangent line at a point where its concavity changes from upward to downward or from downward to upward, then the point is called a point of inflection. So a couple of property of the point of inflection. So say you have some point C, f of C, and we're saying that that's a point of inflection of the graph of f. Then either f double prime of C is 0 or f double prime of C is undefined. Okay. So we're saying that if you have a point and you claim that it's a point of inflection, basically we're saying that's like our critical number of our f double prime. So you can relate it to that. But yeah, so if it's a point of inflection, your double prime evaluated at that point will either be 0 or undefined. Let's look at example 3. So example 3 wants us to discuss the concavity of the graph of f and find its points of inflection. So we're given this f of x. So we're going to do the same process that we did for example 2. So example 3. Again, we want to discuss the concavity of the graph of f and find the points of inflection. So we're given this f of x equal to x to the 4th plus x cubed minus 3x squared plus 1. So again, if we're talking about concavity, we need to look at f double prime. So our f prime is going to be 4x cubed plus 3x squared minus 6x. That's it. Okay. So then if we look at f double prime, it's going to be 12x squared plus 6x minus 6. So again, we need to set f double prime to 0. We need to find the values of x that makes this function either 0. It's not going to be undefined because this is a polynomial. It's not a fraction. It's not a radical. It's just a polynomial. So it's going to be continuous over all reals. So we're not going to have any x values that makes this undefined. So let's set it to 0 and solve and see what do we get. So if we have 12x squared plus 6x minus 6, if you set it to 0. Now, if we're going to solve for x, let me see. We can factor out a 6 from all of these terms. So first we'll have 2x squared plus x minus 1 equal to 0. I think in the last class I did a factor like this, and I forgot that you could factor out like I just did the 6. So, but now you see we still have this coefficient that's not 1. So again, I'm just going to do what I did and show you how to factor that. So again, normally if you want to go from the form we have it in to some form like this, equal to 0, without having to guess and check for those first couple of x terms, there actually is a process or a methodology. So usually for these numbers that will go on the right, we're looking for something when you multiply it gives you this and add gives you this. The only change is you got to find two numbers that when you multiply, instead of giving you -1, you need -1 times 2, which is -2. So if we list out the product of -2, that's going to be 1 times -2, or -1 times 2, and that's it. So now we're looking for the line that adds, when the two numbers when added together give us a +1. So that means we're going to choose this line here. Okay. So again, if our original is 2x squared plus x minus 1, we want to factor this. So I'm going to split